Welcome to The Explainer. Today, we're diving into the story of a huge leap forward in computing, the very first real bridge between human language and machine logic. And it's a revolution that was sparked by a brilliant mind that history, well, it kind of forgot about for a really long time.
So to really get why this was such a big deal, you gotta understand the problem, right? Just imagine you've got this incredible new machine, a computer, but there's no intuitive way to tell it what to do. I mean, where would you even begin? In the very early days, with computers like the famous ENIAC, programming wasn't about typing on a keyboard. No. It was this intense physical job. You were literally plugging and unplugging thousands of cables and flipping countless switches by hand. The wiring itself was the program. It's kind of wild to think about.
Okay, so then things got a little better, thanks to pioneers like John von Neumann. We got the stored program computer. And finally, you could actually write code. The catch? The only language the machine understood was pure binary. Just a long, unforgiving stream of ones and zeros. If you got one digit wrong, your whole program could fail. And good luck trying to find that one tiny mistake. It was a total nightmare.
So who was going to solve this massive problem? Who could build that bridge between human thought and all those ones and zeros? Well, it wasn't some world-famous professor. The answer came from a brilliant 24-year-old mathematician working in London, a woman named Kathleen Booth.
So back in 1946, she was recruited by a Dr. Andrew Booth for his ambitious project at Birkbeck College. They were working on one of Britain's very first computers, the ARC, and Kathleen's deep understanding of how that machine's hardware actually worked made her absolutely essential to the whole project. A year later, something happened that would change everything. Kathleen and Andrew took a trip to the United States. They went to visit the legend himself, John von Neumann, over at Princeton. They were there to soak up the absolute cutting-edge ideas in computer theory, and it was during this trip that a powerful new idea started to click into place. As she was taking all of this new information in, Kathleen started thinking about a truly revolutionary question. What if programmers didn't have to fight with these long strings of numbers? What if they could use simple, memorable words to tell the machine what to do? And this right here just shows you how brilliant the idea was. Instead of forcing a person to remember a complicated binary code like that, you could just write MOV, as in move this piece of data. It's simple, it's elegant, and it completely changed the game. She called her system contracted notation, and she published it in a report way back in 1947. But her genius wasn't just in coming up with the language. She also figured out that you'd need another program, a translator, that could turn her simple words into the ones and zeros the machine could understand. Today, we call that an assembler. I mean, her idea was profound. It was the very first layer of abstraction in programming. But, as often happens in the world of science and invention, she wasn't the only one thinking about this stuff. And the story of who got the credit, well, it took a bit of a turn. So look at this timeline. Kathleen published her core ideas in 1947. Almost 2 years later, a really brilliant team over at Cambridge University developed their own assembler. The thing is, they published more widely, they coined the actual term assembler in the first ever programming textbook, and because of that, they got the official credit. A member of their team, David Wheeler, even got a prestigious award for it years later. Okay, so now that we have the full, complicated origin story, let's take a closer look at the actual concept she pioneered, which we all now know as assembly language. Think of assembly language as that critical, human-friendly bridge to the machine's native language. The key thing you have to remember is that it isn't a universal language. Nope. Every type of computer processor, every architecture, has its own unique assembly language that's tied directly to its specific hardware. So the whole process works in 3 basic steps. 1, a developer writes code using those simple commands. 2, that code is fed into an assembler, the translator Kathleen envisioned, which turns it into machine code. And 3, the computer executes that code. The simple flow freed programmers from the misery of writing binary by hand and made software development so much faster and more reliable. So you might be thinking, okay, cool history, but do people still use this stuff? And the answer is a definite yes. While yeah, most programming today happens in high-level languages like Python or Java, assembly is still absolutely essential for anything that needs direct control over the hardware and has to be as fast as possible. We're talking device drivers, the little embedded systems in your microwave or car, and even classic 8-bit video games that had to squeeze every last bit of performance out of old hardware.
And for Kathleen, inventing assembly language wasn't just a single flash of brilliance. It was just the incredible start to a long, trailblazing career, where she just kept pushing the boundaries of what computers could do.
So after her huge breakthrough, she married her colleague Andrew Booth. Then she got a PhD in applied mathematics because a computer science degree didn't even exist yet. She co-authored one of the very first books about programming, and she was the first woman to do so. She helped start a computer science department, and get this, she wrote a program to simulate a neural network all the way back in 1959. Talk about being ahead of your time. Kathleen Booth lived a truly full and remarkable life. She literally witnessed the entire history of the technologies she helped create. She passed away just a few years ago, having reached the incredible age of 100. A centenarian who saw the world transform from being programmed with cables and switches to the supercomputers that we all carry around in our pockets today. Her story, once lost to the footnotes of history but now rightfully being celebrated, really makes you wonder, doesn't it? How many other hidden figures are out there whose foundational work, whose brilliant ideas are we still overlooking in the history of the technology that shapes our entire world?